So let's continue with from where we left on the earlier class on deep learning, and I would now be discussing about basically a bit of historical perspectives and what we call as a family of deep learners over here. Now for that, let's look into how deep learning came into its origin and how it was growing up. So now for that, the very simple term is that this is not something which just came up in the recent past. It has been there for quite some time now. So we started with around the age of 1950s when we had these neural networks come up with the initial days, and that's when they started with actually McCulloch and Pitt's model. So somewhere around 1943. From there, we came up with Hebbian rules in 1949 till supervised learning by Rosenblatt in 1958, and from there to auto-associative memory in 1980. And this auto-associative memory concept is something which is much more rampant in use today, and that's what plays down a role into how these neural networks can learn and also understand how to associate certain patterns and with what an outcome is, or where it would be in terms of a deep neural network where it will be learning as to understand what an image for a particular class will look like. So it's going to associate these image appearances to class labels itself. Now in the 1960s was when a lot of neurosciences and biological neurosciences were coming with mathematical discoveries, and both the communities were benefiting each other from each other's work, and that's where a lot of work came down onto how feed forward within multilayer perceptron happens, and can we use them in order to understand how in our own visual perceptions how we perceive objects. So do we do it like it's something like, does our eye look at everything as a camera sensor or a CCD sensor or a CMOS sensor as in a camera, or does it actually have some sort of a processing pipeline within the whole process? So does it sense, instead of images of pixels, is it sensing a array of different directed edges and gradients, and then is our brain reconstructing the way we look at the outer world together? So this was the work which went down around 1960s, and from there till 1980s we had this new term called as neocognition, and what that meant was a new sort of networks started coming up which were called as convolutional operations networks. Now if you look at the network which we were looking in the earlier class, so we just were connecting all neurons to all neurons. Now instead of connecting every neuron to all the other neurons in the subsequent layer, if we can define some sort of a convolutional operation. So say I have a weight vector which can translate in sort of a sliding window fashion. So now on my first input node, if I have say something 441 such nodes, and I want to connect it to my second hidden layer, to my first hidden layer which has about 400 nodes. Now instead of how many connections I can draw down is basically 441 connections to each of these nodes, and similarly so this will form down a matrix of 441 cross 400, which is the translation which goes down. Now say instead of that I take down a small set of vectors, and this is called as a convolution kernel. So I have just a convolution kernel of size 5, and say I can convolve this and pass it over the whole thing. So I can define the output of my first input nodes to the hidden layer in terms of a convolution. Now the number of weights I will have to look over here is actually much lesser, because it's no more all the connected weights over there, but the number of weights is basically 5 which is left down. So the number of computations go down, and again the beauty of convolution, which is making it space invariant, comes into over here. So in terms of understanding whether an image has say for our case, if it is an image of a cell, so now whether the cell is present on the top left corner or the bottom right corner, it's invariant to each of them, because I will just be convolving with these kind of weights over the whole image. I will be able to find out the features of the image wherever the object be located over there. Now these were the new concepts which were coming down around in 1980s, and from there came down another interesting concept called as max pooling, which is to reduce the complexity of networks, and from there we came down to another interesting concept called as backpropagation, which is about how can we take the error back behind over there and do it. So this is what we were using in the first lecture on neural networks itself for training a neural network, and coming down to what is the optimal weight combination. Now sleek from there to 1980s from 1980s to 2000 is when a lot of research went into understanding simple low complexity problem solving with these kind of networks. So that led to the birth of recurrent neural networks, then long learning feed forward neural networks. There was advanced gradient descent sequential network constructions, which is how they can be constructed one by one at a time, and from there to a very famous thing called as an autoencoder, and from there a backpropagating CNN, which was a very fundamental discovery. And in fact the exercise which we do later on will have a backpropagating CNN itself for solving the same kind of a problem. So sleek from there to 2000 and onwards, and this is where we land up beyond the era of beyond the era of neural networks, standard neural networks, and into the era of what we called as deep learning. And where it started was with one of these kind of deep neural networks winning the NIPS 2003 challenge on feature selection, and LeCun's very famous model of the digit recognizer called as a LayNet, and similar like what we are going to use later on for our problem as well. So from there to deep Boltzmann machines and autoencoders. So right from there, around in 2006 onwards, we saw a major boost in the way deep learning was being done, because if you look over here, typically these networks have a lot of connections between them. So the number of multiplications, the number of nonlinear operations you are going to do is actually seriously large. It's not a very small number. So you need a good amount of computing power available at your space to do it, and say with a desktop computer it would never be possible, finitely possible. You would actually either be needing a lot of RAM space, and in any ways your process power is always limited to one single thread, or maybe for certain machines which have hyper-threading support on them, you can have multiple threads up to 4 threads or 8 threads or in total. Now even with them, the total time you would be taking is going to be finitely seriously large. Now with advent of these GPUs, and what NVIDIA got down in the recent past is they upgraded their gaming cards with cores present over there using specific library called as CUDAs, where you can use all of these cores as compute cores for solving the purpose. So we have specific libraries called as CUDNN libraries these days, which help you in creating a neural network on the gaming card itself. So you can just buy a simple gaming card for less than 10,000 Indian rupees and use that as a supercomputer attachment onto your desktop computer and train down networks much faster. So we will be doing exercise later on in the day where I am going to use a similar gaming quality graphics card as a GPU alternative, and we are going to show basically how fast we can learn the whole network. So from there till 2009 we got down this deep belief network on the GPU, which was a seminal contribution to max pooling and CNNs on the GPU, which required a significant amount of efforts in terms of the VLSI design constraints within how GPUs are designed. And in 2012 with ImageNet winning the ImageNet challenge from Alex Krivsky with the AlexNet is where it actually made the whole community come down to a consensus that deep neural networks are what is going to rule down substantially the field for a longer period of time now, and this is a sort of a framework which can be used as very feasible solution to a lot of problems we were facing. So instead of each of us trying to work on a different area and arguing across as to which is more important, whether a feature extraction is more important or classification is more important, or who is at a much more superior phase, the whole community now comes to a consensus that let's understand that it's a hierarchical problem, let's put the whole hierarchy into one single place, and let's take one single model which can learn the hierarchy and solve the problem. And this is what we are going to speak. Now if you look into deep learning, you basically have a family of learners over there. Now the first family is called as the fully connected network family, and this is similar to a multi-layer perceptron. So what happens is that each neuron on any layer is connected to every single neuron on the subsequent layer of the hierarchy. So the first model is an autoencoder, which learns to basically encode and decode. So to put it in very simple terms, it's basically you take an image patch, you feed through this network, at the output over there you should be able to reconstruct the same image patch. So if I have a 5x5 patch on which I see an apple, on the output also I should be seeing the same apple coming down over there. This sort of a network is called as an autoencoder. It makes up of one part which is called as an encoder and another part which is a decoder, and since it's encoding itself, that's where the name comes down. So then we have a stuff called a stacked autoencoder, and what does this is basically you stack down one by one autoencoders together and you create a much deeper network, and that's where it gets its name. Next one is a sparse autoencoder, where what you have is basically that we had seen that particular problem in the last class, where we were trying to solve down pixel level labeling problems on the optical coherence tomography images in order to find out which pixel belongs to what kind of a tissue. And on the second layer over there, we could see that most of the values were zeros. There were some values which were just ones or minus, a very high negative value over there. Now this kind of a sparse autoencoder is what is going to help you in finding out, imposing that kind of a sparsity constraint over there. Then there are denoising autoencoders which you can use as denoisers actually. So if you want to remove noise from a certain kind of an image without you knowing that what is the distribution of the noise or what is the basis function of the noise, you can actually learn them using a neural network and very easily remove. And in fact, you can remove those noise of very complex nature. So there can be Gaussian and a speckle noise, there can be Poisson and a multiplicative noise together coming down, and you can denoise these kind of images by learning them appropriately. From there is a convolutional autoencoder, which is a mold between convolutional neural networks and an autoencoder. So basically each layer of the autoencoder is a convolutional function itself. So that does not typically qualify as a fully connected network, but again, since it comes from the family of an autoencoder, we just keep it over here for the same purpose. From there, the second one on fully connected networks are belief networks, which consist of restricted Boltzmann machine and deep belief network. So a deep belief network is basically sort of a stacked version of the restricted Boltzmann machine itself. And as the name suggests, Boltzmann, so this is what has a Boltzmann distribution imposed over there, and you can have very good amount of memory associativity within these networks. Now you can read about details of them in much specialized literatures, but for our stuff we will just keep them to the minimum. The next family is convolutional neural networks. So in convolutional neural networks, you can have generalized conv nets or very specific models which have come out in the recent past. So some of them are called as LayNets, GoogleNets and AlexNets. So LayNet is again from that MNIST challenge with Jan LeCun was solving in 1998, and so they have a much improvised version on top of that from Google, and that's called as a GoogleNet. And the ImageNet challenge being solved by Alex Krivsky is what's called as the AlexNet. Then there are UNets and ResNets, which are basically networks where you can put a whole image and get down the segmentation of the whole image instead of doing it as a pixel by pixel manner, and every single layer over there is implemented as convolution functions. From there we have recurrent neural networks, and one very famous component of that is long short-term memory, which can try to encode temporal patterns itself within a network. So if you're looking at say temporal data, which is say there are scans of cancer patients every 6 months of the same person. So if you want to relate between the temporal side of it, the same voxel at the same space on the same patient, but every 6 months, and you want to do a follow-up, so you would be using some sort of a temporal mapping, and that's where you would be making use of LSTM like networks. So let's get into a few of these places where deep learning is playing a big role today for medical image analysis, and that's what the whole agenda of our discussion is. So the first one I would like to point out is this particular paper from PAMI in 2013 on one of the special issues on deep learning, and this was about organ detection in MRI, and a very clear case in which the idea was that can each pixel over an MR sequence, so if you have one of the slices in say a T1 sequence or a T2 MR sequence, then can I label each single pixel as to it belongs to which particular kind of a tissue or which particular kind of an organ. So there were manually annotated examples which they were using, and the solution was not a very computationally complex solution. So it was just a very simple stacked autoencoder which was doing unsupervised feature learning, and finally at the final stage it was mapping them down onto which particular organ it belongs to. So this is a very seminal contribution which came up, and the way this whole learning was done without having to handcraft and hand engineer features was seriously wonderful contribution at that point of time. There was transactions, IEEE transactions on medical imaging special issue which came out in May 2016, which speaks about all on deep neural networks. So this was just a special issue which had all papers where deep neural networks were being used to solve medical image analysis problems in total. So that ranged from microscopy to MR to brain to histologies to robotic surgeries, everything over there. So it's a good collection of papers which I would definitely add as a pointer for you to go through if you are trying to make sense of where and how people have been using these kind of techniques in medical image analysis itself. Now, first few snapshots from the issues are where on brain tumor segmentation using convolutional neural networks, then on using deep 3D convolutional encoder networks with shortcuts for multi-scale feature integration for multiple sclerosis detection and lesion segmentation in brain MRs, and then there is another one on automatic detection of cerebral microbleeds from MR images using 3D convolutional neural networks. So this is where we are no more limited to images or 2D, but since the data is inherently 3D in the voxel space, so we are going to use all of the voxel information and design a neural network which is also operating on the voxel space. So earlier, if we had a small patch of 5 cross 5, then I just have 25 pixels, and my convolution operator may be another smaller one which is operating only on the spatial scale. Over here, I will be having now, instead of 2D scale, I will be having a 3D volume. So I will have a 5 cross 5 cross 5 voxel space, which is 125 voxels. So now I can define a very small convolution operator, say maybe 2 cross 2 cross 2, which is just 8 elements over there which can move in the voxel space and do convolutions over there. So this is what brings in the beauty and some novel changes which the community itself had to do. If you look at computer vision community as such, that's not where we operate on 3D data day in and day out. It's majorly 2D data which has a time axis to it, but over here it's majorly 3D data. Although at some certain point of time, when you are trying to do a dynamic MRI kind of stuff, you would also be getting a 4D data where it's 3D data over time, so you have 4 dimensions. So that's where you would bring down much more novel contributions as to how can these modeling be done, maybe with 4D neural networks or something even beyond that and much more radical and interesting. So from there, I would point out to one of the earlier work which we had presented sometime early in 2016, and this was about a concept called as distribution preserving autoencoder. Now the beauty over here is when we were telling about these autoencoders, and the concept was that I wanted to always preserve the same patch. So whatever goes in my input, the same has to be created on my output, and that is what I would like to look at it. But if you look at speckle images, then you would not necessarily have one-to-one mapping, because speckles are necessarily spatially non-stationary. So they don't remain stationary in space when you are taking it over multiple points of time. So, but however, the only thing which is constant for them is that the distribution, they come down from the same sort of a distribution. So what we wanted to do was, can we create a network which can learn to encode in a way such that the output has the same distribution as the input. So this is what we were doing with distribution preserving autoencoders, which paved a very great way in solving a challenge about plaque detection in optical coherence tomography images. So we could very effectively delineate plaques, and this is one of the 3D visualization. So we have this whole model running on a frame by frame basis over a whole pullback of cardiovascular optical coherence tomography images, on which we find out these plaques and then how the whole 3D topography is mapped down over there. So you can have a careful look over there as well, and this is a model which is pretty simple to implement, does not take much of compute time requirements during testing. However, the cost functions and everything is definitely something where we had to put in a lot of way in which how the data transfer happens and how the networks are gone. So what I wanted to basically say through these ones was that it's not necessary that you will have a one-shot single go implementation where you can just take a model and do it. A lot of times you will have to innovate yourself. You will have to create your own networks, own training function cost measures, as we had done over here. So instead of taking a mean squared error or sum of squared errors over there, we thought of taking down a divergence measure so that we map down distributions between each of them. So these are new innovations which come down when you are trying to use neural networks, and specifically deep neural networks, for the area of medical image analysis. Now with this, we are almost at the end for deep neural networks, although it's a very interesting topic, and it would have been fun to devote many more hours onto this one, which itself is a much more specialized topic, but I'm just over here to give you an introduction and some user case scenarios where they are working. So Here when we come down to an end, I have this famous quote by Trishul Chilembi, and he says that this deep learning thing is quite like quantum physics was at the beginning of the 20th century. And I just leave it up to you to figure out why does he say something like this. And now the reason why he is saying it is because if you look at quantum physics at it was at the beginning of the 20th century, then there were a lot of experimentalists and practitioners who were ahead of it and who were ahead of the theoreticians. So it took a lot of time for theoretical physicists to say and explain each and every single stuff about quantum mechanics, whereas experimental physicists were observing it much faster. So today with deep learning it's the same thing. When we look into the theory of deep learning, it's really complex to understand and explain over there, and without those explanations possibly it's really hard for you to even make a way through in terms of publication or even a single product development over there, because until you are able to explain the theory there is no surety about why it's working the way it's working over there. Whereas in practice we do see a lot of things just work like magic and as a black box. And this is a point where I would definitely leave a thought for you, that just don't trust it as a black box. Try on innovating over there, and please make a sense of understanding why your method is working the way it is supposed to be working, or why it's not working the way it was supposed to be working, which you had desired. Now that takes us to the end of it, and I just have a take home message over there. So as far as working with deep learning, and if you want to do some serious amount of work, then you would possibly need a custom designed workstation which is with a GPU, and although I'm going to demonstrate it with a very simple gaming grade card, but it's generally suggested that for most of our serious experiments we do use a GTX 10X grade of card or a Tesla K40, and so there is an M40 which is also over here now, and you have the P100 GPUs coming out, or you can use much more affordable version of them on a GTX 1080 or a GTX 1060 as well. And if you can really afford, then DGX1 is a deep learning box, a single box solution which is provided by NVIDIA, and it's great for doing it. On the toolboxes side of it, you can use Theano and PyLearn 2 within Python for deep neural networks. On a separate language called as Lua, you can use the library called as Torch. For NVIDIA things, you would be requiring CUDA, digits, and CUDN. And in fact, like if you want to call down the GPU through any of these, either from Python or Lua, you will still be requiring CUDN and CUDA. If you're not a much fan about these large object-oriented programming or complex languages, you can still choose to stay with your very homely, comfortable environment of MATLAB. So just GitHub for the deep learning toolbox, and you will be getting down a very sweet link coming down over there, which you can use for learning deep learning. And in fact, MATLAB 2016 onwards, within the neural network toolbox, you also have autoencoders and CNNs as a standard package and feature available. So do feel free to visit them and make use of them. And for reading more about deep learning, there's a website where we have a ebook for deep learning available now. So that's written by the major players on the field. You can visit deeplearning.net, which is a major website where we socialize and all new postings in the field of deep learning come up. And beyond that, I would suggest that you read this. You can have a good read over this overview paper, which provides most of the materials which we have been using for these lectures. And you can also have a look through this particular book on deep learning methods and applications. And for looking at conferences, ICLR and NIPS are the places where majority of stuff related to deep learning are published. So with this, I come to an end of the theory class, and we would have a small demonstration with solving the same ALL problem on using Torch on Lua for our deep neural network implementation. So we get back to the practical demonstration of using a deep neural network, and we will be using an architecture called as the LayNet in order to solve this problem. So what we would be doing is we are again going to use the same ALL IDB images which we had downloaded in the last example as well, so that I can explain you the whole concept over here. Now on top of that, our deep learning purpose will be solved using Torch, which is a scientific computing framework which is based on Lua just-in-time compiler environment. So you can just go down to the website called as torch.ch, and you would be ending up on this page. Only reservation over here is that this is available for Linux based systems. In Unix based systems it's very easily compiled, so you might need to have a Linux based system available over there. Now they provide a very simple step-by-step pause if you want to install Torch on an OS X platform from Mac or on Ubuntu as well. So what you can do is you can follow down each of these instructions over here and just keep on doing. You would this would be downloading about 2 gigs of data through your network, so you need to be at least available with that much of bandwidth from your side. And once you are able to finish till this bash rc thing, and just as a word, this would take you some amount of time. So typically this git clone and the recursive cloning over there, and then the installation, this takes you roughly 30 minutes based on what kind of a bandwidth speed you are affording over there, and then the whole installation completes. Now once you are over here, what you can do is after that, if your system has a GPU, which I would strongly recommend, is how we are also going to do over here, then you would need access to the NVIDIA CUDA toolkit in order to use your GPU and make it faster. So today the CUDA standard is CUDA 8, so you can just Google down for NVIDIA CUDA toolkit, or just go on developer.nvidia.com/CUDA toolkit, and you would be getting access to that. So on the CUDA 8 toolkit, you can just press on download over here. Now this goes down to another page on which it would ask you basically a few set of questions. You can select your system, say Linux, and then it would be asking you another set of questions as to what is your processor architecture. For most of us, it would be an x86 or a 64 system. So I click on this, and then it asks me another question as to what sort of OS I'm using. Most likely we are going to use Ubuntu, at least for my system it is that. I prefer using the 14.04 because of a lot of support issues around with other software pipelines as well. So I have this 14.04, and I also prefer using the Debian distribution file on a local one instead of a run file or any of them. So just click on this and you would be directed to a download link. So now you can download this 1.9 gigs over here, and once the download is complete, you can just do a dpkg and load this one onto your apt-get repository, and from apt-get now you can basically install CUDA. So this is also going to take you, so apart from this 1.9 GB during the update process, it would be taking about a couple of hundreds of MBs as well on the download. So and then it takes about roughly 2 hours of a time from getting Torch till CUDA and everything downloaded. Now beyond that, you can also install CUDNN if you would like to use CUDNN features as well. Now that's something you can just Google and find out for more of details as well. Now let's get down into the actual part of the stuff. So what we have done is we had our data set over here. You had seen these images over there. Now all of these images, we have actually packed them onto some sort of files which are called as .t7, which is a standard extension for Torch version 7. So we will be loading down our pre-formed data. So it generally takes a longer amount of time to load each image at a time. So what we have done is we have transformed that into some sort of a matrix and stored that as a data file. I will just load one file and I get an array of all the matrices. So in Torch we call it as a tensor. So we just have a 4D tensor in which my first dimension is basically the image number which I am going to get. The second dimension is each of these color planes. The third dimension is the rows, and the fourth dimension is the columns. This is how Torch natively handles it out and how we pack down the data. So we will be providing you with small MATLAB codes on how to create these .t7 files as well, and I'm not discussing it any further now. Now from there, let's move into our network over here. So this is a standard code on Lua, how it would be looking like. So you have certain kind of files which you would be needing to call. So we are using a CUDNN library as well. So I'm calling down NN, which is for defining neural networks, and then I do a require for CUDNN because I want accelerations on this CUDA and with the CUDNN library itself. And GNU plot is for basically I want to plot those fancy epoch versus error rates one. Now this is a place where I'm just loading out all the data. So I have my training set, I have a validation set, and I have a test set. This training set is where I take all the training data on which my errors would be computed and I would be doing the backpropagation. I take a validation set in which what I would do is basically that's a set which is not used in the training, but every epoch I push this set in order to find out what is my error, and I can use that error in order to find out to a closing point of where I need to stop training any further, and test data set is what I would be using subsequently after that. Now from there, what I do is I have my network defined in a separate file which is called as lanet.lua. So this is where my whole network is defined. So what I have is spatial convolutions over there. So I have 3 channels which are my 3 color channels mapped onto 6 channels over there. So there are basically 6 convolutional operators which I am going to define over here, which takes in 3-dimensional input and does it, and each of them is a 5x5 operator. So I have a 5x5 cross 3 sized convolution kernel and 6 of such kernels being defined over here. Then I do a nonlinear transformation in terms of ReLU, which is called as a rectified linear unit. So the only difference it has is basically if a input to the ReLU is negative below 0, then it clamps it down to 0. If it is positive, then it just keeps the same positive value passing. This is also another sort of a nonlinearity. Then we do a max pooling over there over a 2x2x2x2, which means that I take a 2x2 area and then I push it down into one area. So a 2x2 basically 4 pixels. Whatever is the maximum value in this 2x2 element, this is what is stored into one single pixel a region over there, and then I make this one move by a factor of 2x2 such that I have non-overlapping max poolings coming down. So on this output over there, I will again do a spatial convolution. So what this does is all the 6 channels, because I had 6 channels output from here, so I will be doing a 5x5x6 sized kernel convolution, and there are 16 of such kernels which I am going to learn over here. So similarly, I do all of those operations of max pooling and everything, and here finally what I have is, since I have 16 layers over there, and this 5x5 is again dependent on what was my initial size of the image and how it comes down. So what we find is basically there are 16 x 5x5 such. So it's basically what comes down at the end over here is 16 such 5x5 patches, and I just want to linearize all of those neurons into one single layer. Now after having done this through view, I have a linear connector between this number of neurons to 120. So I map them to 120 hidden layers over there through via ReLU, and this is the fully connected, no more convolutional operations over here. And then from those 120 to 84, and from there again to 2, and then I do a log of softmax as a nonlinear transformation over there, and this is what defines my lanet architecture totally. So this is what I load over here. You can actually copy paste the whole code over here and define it and do it, but we do it just to keep the training part separate and the model part separate, and it helps us in much better bookkeeping. So now what I do is I convert this model to CUDNN and typecast this as CUDA, so that I have all the operations available as CUDNN module and on CUDA memory space as well. I define a criteria which is my loss, and this is a negative log likelihood criteria, which is my classification error. How do I define it? And then what I do is I also need to evaluate this criteria on the GPU itself. So that's why I'm going to typecast it as CUDA, so that my parameter space exists on the GPU memory itself. Then what I do is I set a learning rate over there, which is 10⁻⁻², and total number of epochs over which I'm going to train. I'm putting a very smaller value over here as 10. Now what I do is I take my data set and just look into how many samples are present over there. So use the size operator to look into how many samples. Then I define 2 local variables which are just training error and validation error, and eventually what I do is over 1 to total number of epochs, I'm just going to iteratively process this one. So for the first epoch, what it would do is initially it would take since it has multiple number of images over there, so it's going to take one image at a time and then compute and then reiterate this whole process the way which we are learning over there. So it takes in the data and then it does a feed forward through the whole thing and evaluates what is the error, which is what happens over here. So you do a forward of the model. So you have certain weights over there, you put in the data, you are going to get down certain output. Now what you do is you take this output and you know what is the target. So you can do a forward on the criteria and find out what is the amount of error which comes down over here. Now what you do is you zero down all the gradients which were earlier computed, and then you do a backpropagation through this part over there. So what you do is you backpropagate and find out what is the total derivative across the error, and you also backpropagate this one across the model cumulatively, and then you update the parameters of the model using this particular learning rate. over there. Now after this has been done, you can find out what is your total training error over there, and this is where it keeps on accumulating and coming up. Next what we do is we move a bit below and we find out what is the total amount of training error by just taking an average over the total number of training data over there. On this side of it, we are also going to find out what is my total error in validation as well. So I use the validation set over there, do a forward and the same way, and then find out. But this is no more being used in order to backpropagate, so I don't have an update mechanism over there. Now once that is done, I will be plotting. This is a small module with GNU plot in order to plot the errors over there. Then over here I'm going to test it with unknown data. So I am just going to typecast them onto CUDA and then just do a forward of the model. Now once I am able to do a forward of the model, I am going to get down my predictions. Now note that since it was a log softmax, so I needed to get an exponentiation of the whole thing. That's why I am doing an exponential over it, so that I get in the range of 0 to 1. And once that whole thing is done, now I am going to get down my predicted values and predicted class, and this is what I am going to print over there. So let's jump into how we run it down. So typically for running this kind of code, you will be so I have already rooted into the folder where my codes are located and my data. So this is where my code and my data is located in terms of these T7 files, such that it can load it very easily. So over there I will just write down a small command called as th, which is function for calling down the torch compiler itself, and then say that this is the file which the compiler has to execute. Now once I do that, I can press an enter. So that starts with executing. You can see that it's loading the data, and then it's able to process out all the epochs over there. And on the validation side over there, you can see that these are the predicted classes. So the predicted classes, so since we had put down some 10 samples over there in order to see how the predictions were. So the first one got predicted properly, the second one there was an error in prediction, the third one was correct, fourth one was correct, fifth there is again an error, sixth it is correct, seventh it is correct, eighth correct, ninth, eighth there is an error, ninth is correct, 10th is correct, and 11th is correct. So like also for 11 of these classes we could see all of them, and this is a plot which I got from my GNU plot about the total validation. Now if you see that this curve is actually still falling down, it hasn't yet saturated, so maybe I can put it down for a longer number of epochs, maybe 50 epochs or 100 or 1000 epochs at a lot of time, and then if it comes down to a much lower error, because the total error over here is still at the range of 0.5, so we would typically prefer this to be in somewhere in the range of 10 power of minus 2, and that's where we expect that a lot of these predictions would be correct. So you can just have a play around with these ones by increasing the epochs as well, and till then, thank you.